Okay, so thank you, Mary, for providing us the context of the policy. And maybe people did catch that there's some basins in Siskiyou County and Shasta County, this northern hydrologic region, but a lot of this region is volcanic and not included in those alluvial basins. So I'm sure you'll have questions on that for Mary when we get to the question and answer period. So now we're going to change gears from the policy and start looking at the science. And we're very lucky to have two people travel from Livermore today to give us presentations on the science. The first is Lee Davisson, who is a research geochemist who for the past 25 years has applied his water chemistry, isotope tracing, and groundwater age dating skills to the management challenges encountered in Western water. No large task. Experiences range from characterizing remote groundwater basins of California and Nevada, imaging groundwater in the Central Valley to quantify water quality impacts, detailed mapping of groundwater flow paths beneath urbanized areas for water recycling projects, and developing and applying tracing methods to determine sources of dissolved salts and organic matter in rivers and groundwater, including produced water from oil and gas wells. Lee is currently president of ML Davisson and Associates Incorporated, a water resource and water quality services company, and is a licensed professional geologist with the state of California. He currently has 30 peer-reviewed publications in the field of hydrology and environmental sciences, including book chapters on isotope hydrology applications. Lee also has extensive experience linking water quality with land use and predicting fate of contaminants. So he is going to give us an overview of the Northern California Cascade region hydrogeology. Thank you.
Thank you, Mary, for that introduction. I'm always pleased to come up here and give a presentation. Everybody hear me okay? Since I don't have a pointer, I may get a little animated here and have to shout at you guys, so if you don't mind. Nevertheless, who was here last year when I gave a talk? So some of you are familiar with that, and maybe you'll hold me to some of the comments I made last time. Nevertheless, I'm going to attempt to give a summary of the hydrogeology up here and its unique characteristics in a short amount of time. If those who were here last year remember, I think I was up here for about an hour and a half presenting and another hour and a half of answering questions. So I'll do my best to try to give you a good understanding of hydrogeology. I'll start here with Bulletin 118's Northern California Groundwater Basin designation. This is an important thing to point out because it points out a contrast relative to this area and what makes it unique. First and foremost, in green here are the designated basins. I don't have them color-coded for prioritization purposes, but only to delineate their boundaries. Probably the most important thing for illustration purposes is the northern part of the Central Valley. And this is a classic alluvial type of basin. It's made up of stream flow deposits. They range from clays to cobbles or even boulders in some cases. And in this alluvial material, you tend to have a very high porosity and a modest permeability. Permeability is the ability for the material to conduct water. So there's interconnectivity between the pores typically, and these tend to be very productive aquifers in the state of California and other alluvial systems throughout the world. Groundwater wells drilled in these alluvial basins tend to be highly productive, in the hundreds to thousands of gallons per minute. and sustain a lot of our irrigated agriculture in the Central Valley. Now, there's a unique feature up here, circled here in the purple circles, and these are first magnitude spring systems that emerge from the base of volcanic deposits in the major drainages of the Sacramento River. When I say first magnitude, typically a spring that is greater than 100 cubic feet per second is classified as a first magnitude. We can also take a system of springs that are all in the same location and call it a first magnitude spring system. And the unique thing about these is that they all emerge from hard volcanic rock and appear to be completely separate from any alluvial systems. And pictured here, upper left, you've got Mossbrae Springs. On the right, we've got Rainbow Springs, the Fall River. Lower right, we have the rising river of the Hat Creek system. And then in the lower left, a truly unique spring system that emerges literally from the hillside at very high volume, big spring in the McCloud River. And this forms the majority of the McCloud River flow, base flow. Now, it's important to point out that these systems are made up of very young volcanic rock. This volcanic rock tends to be highly fractured, and it has a very high permeability, but it has, in contrast, a low permeability, just by virtue of the fact that it's large blocks of rock that have no porosity in themselves, each block, but it's all the fracture material in between the blocks that form the permeability structure and what smaller porosity exists. And so you can see from this picture here, this is a highly permeable material. In strict contrast to the alluvial type of basins that we're used to. And for the matter of fact, most of groundwater science historically has been built up based on the alluvial basin type of deposits. So there's some structural styles characteristic of young volcanic systems. Two that I'll just point out here that are relevant in this area. On the left is a typical shield type of volcano. This is the Hawaiian style volcanic deposit. This is made up of basaltic material, which tends to be low in silica when it erupts, and so it tends to form rivers of lava. I'm sure you've all seen pictures of this on TV, or maybe you've actually been there and watched one of these things. Nevertheless, it's not uncommon to find lava tubes forming. You've probably seen some images of this, that you'll form a hard crust with cooling lava, but underneath you still have an underground river of lava flowing through. Eventually those exhaust themselves and you vacate that lava tube, you're left with an empty tube. And these are buried in the subsurface of these basalt-dominated volcanic deposits. On the right side is a classic composite-type volcano, which is Mount Shasta, as an example. And this is formed with a combination of different volcanic deposits, but on average tends to be a little higher in silica. It's a more viscous lava, and so you tend not to get rivers of lava flowing. You tend to get more short geographic extent of lava deposits. Those cool, shrink, and they crack, and you form extensive parting delineation in the permeability structure. On the lower right here is Bernie Falls. Has anybody never been to Bernie Falls here? No? You know what you're going to be doing this weekend. You got to go there. Nevertheless, if you look down below, here's one to jump up here. Can everybody hear me okay? That's Hat Creek flowing over the top. But you can see these are a series of spring discharges along parting lineations in the layered volcanic rock there. So go down there and take another look at Bernie Falls, and you'll see those spring discharges. You're literally looking at groundwater flow in these kinds of systems. So, in short, we have 3 volcanic centers. We've got Mount Shasta, Medicine Lake Volcano, and Mount Lassen. And circled in purple there are the major spring systems that are discharging at the downstream or down gradient areas of these volcanic edifices. They form the base flow of the Sacramento River, the McCloud River, as well as the Pitt River. And if you look in all told, you can basically find that it averages about 3,000 cubic feet per second. Okay, and that's a lot of water. As a matter of fact, that equates to nearly 2 million acre feet a year just emerging as base flow from these springs. And you can fill half a Shasta with it. And so this in and itself is an appreciable amount of water that is just coming out of these volcanic systems each year. That doesn't mean that it's 2 million acre feet just stored in those aquifers. There's probably a lot more park behind that. And so there's a lack of information exactly what is the extent of these volcanic aquifers and how much storage of groundwater do they have. And so I'm going to take the opportunity here to try to discuss this a little bit further. Just a point of digression real quick. Not only is this water important from the standpoint of the Central Valley Project and storage of groundwater for downstream use in California, but Pacific Gas and Electric generates gigawatts of power each year off the Pitt River and Cloud River hydroelectric projects. And of course, you've got the world-class sport fishing area up here, as well as very unique fish habitat that there's actually ongoing research that's learning some very interesting things about their spawning habits as related to these springs. And so, the very critical resource, not well understood at this point. And so I've been working in the past 20 years or so trying to find opportunities to enhance the understanding of these systems a little bit more. So here's the key issues in my mind that need to be addressed for these volcanic aquifers. First of all, what's the source of the recharge for these aquifers? And what's the nature of their flow paths, which I've elucidated a little bit on that so far. But probably the most important question is how much storage is involved with these recharged waters in these volcanic aquifers. How much water are we really talking about? And this is an important issue because with any kind of land use development that requires groundwater, or more importantly, any kind of long-term variability in our climate, how does that affect the spring discharge and the storage in these volcanic aquifers? And how sensitive are they to these changes? So I'm going to take a moment and talk about one tracer we use to try to determine recharge. That I'm not going to be able to make you educated in exactly how these all work because I don't have the time. But the most important thing is that water in itself has intrinsic properties that allow us to measure natural tracers in the hydrologic cycle. These tracers are derived from natural mass differences in oxygen and hydrogen atoms that form water molecules. And we refer to these natural variations in mass as isotopes. They have a fixed abundance in the hydrologic cycle, but as water changes its physical state from ice to liquid water to vapor, it undergoes a partitioning or a change in the relative amounts of these different isotopes, in the water molecule. And these represent small mass differences that we can measure very accurately using mass spectrometry techniques. And this is an area that's been explored and researched in the systematics of their variability for the past 50 years or better, 50 or 60 years. And so we have a predictive basis to understand where water comes from using these intrinsic tracer properties of the water. And this image here is a contour map of variability in isotope abundance in rainwater in the North American continent. And the thing you can see here is in coastal areas you tend to have these warm colors which represent a higher abundance of isotopes. And as you go up into elevation in cooler areas or inland areas, you get into these more isotopically depleted zones. You can see in the Gulf Coast we have a lot of warm coastal water yielding precipitation, which tends to have a more abundant type of have more abundant isotope amounts, where in the polar regions you have a lot less. So this is a temperature and distance driven process of variability. And so we can exploit that because in California we have not only the coastal region, but we have very steep elevation gradients that promote these variability in isotope abundances. Here is an example from the Mount Lassen Hat Creek Valley area, and this was work done by Tim Rose and myself back in the 90s that mapped out the variability of these isotopes in spring water throughout the Hat Creek Valley and in the Mount Lassen area. And the thing you can see is a regular variability from a higher number to a lower number going from west to east that follows the increase in elevation and distance across the Hat Creek Valley. The sharpest being in Mount Lassen itself, because it's the highest elevation that tends to have the lowest isotope abundances. And we were able to show that the isotope abundance in Mount Lassen was the same as the first magnitude springs of Rising River and Crystal Lake, about 30 miles down gradient of Mount Lassen, and showed that they were related in terms of their source. Another way we can look at this is abundance of the isotope abundance of the oxygen versus the hydrogen. This is a way we graph the data and look at it in a systematic way. We have a reference line that we use to represent all our precipitation worldwide. And the important thing to show is that Crystal Lake and Rising River in red here basically overlies that water that's collected from springs up on the Mount Lassen edifice. And so these are the same waters. In contrast, other spring waters further down gradient. Okay, and it's just a graphical means to show that they're connected. Okay, that Mount Lassen recharges, snowmelt from Mount Lassen recharges the Rising River Crystal Lake spring. Same goes for the Mount Shasta region. In Mount Shasta, we have a slightly different relationship because we don't have long-range basalt deposits. If those of you have been up in the Hat Creek Valley area, you know that there's some lava tubes up there, Subway Cave. We've all been to Subway Cave. We all know that spot. And so those kinds of lava tubes are probably buried up in the Hat Creek Valley and are conduits for rapid infiltration from Mount Lassen. In the Mount Shasta area, we don't have similar features. This tends to be, again, a composite volcano, more short-range type of permeability in the volcanic deposits. And so what you see are sort of a high elevation spring and a lower elevation spring. They're they're separated both in this graphical sense, but also in the map view here. And then you can actually map out the isotopic abundance that you expect as a function of elevation in Mount Shasta. That plot on the lower right is from a USGS study a number of years ago by Davisson, and they showed little local springs have a very systematic variation of isotope abundance with elevation, and then when you compare those to major flowing springs, you see those major flowing springs either sit along that line or off the line. If they're off the line, then it has to do with the fact that they're discharging from a much lower elevation than what they recharge. And it gives you a systematic way to trace elevation of recharge sources. And so an effective way to understand recharge in the Mount Shasta region. And then lastly, up in the Medicine Lake volcano system and the Fall River Springs, this is a recent study that we published last year that compares springs and snows up in the Medicine Lake volcano area with the Fall River Springs area. And those are all clustered right here. So anything you just sample up on top of Medicine Lake volcano basically overlies the Fall River Springs isotope abundances on one of these graphical displays. And that's in strong contrast to groundwater measured up in the Klamath Valley area north of the volcano, which anecdotal information accumulated over the decades suggests that water was originated from up there. But the isotope data prove that that's not the case, that they're a completely different recharge source than the Fall River Springs. So the point being with this isotope tracing approach is to try to start narrowing in on what the basin boundaries are for recharge to these first magnitude spring systems. And here in the white areas is a very generalized view of recharge areas that we've mapped out with analysis we've done over the past 20 years. There's still a lot of uncertainty about all the details there, but nevertheless it gives us a means to start mapping out boundary conditions for recharge, and we compare that to precipitation rates and discharge rates of the springs, and we can start doing some water balance calculations on all these systems. And here's an attempt to do that for the three systems. We have Mount Lassen Hat Creek system on the first line, about 140 square meter or 140 square mile recharge area. We have about 400 cubic feet per second discharge coming out of the springs. An estimated annual precipitation feeding those springs, and then a percent of that precipitation that actually goes into recharge. On the bottom line is Shasta, a similar type of argument. Both Shasta and Lassen yield anywhere from 50 to 60% of its annual precipitation to recharge in the groundwater system. Medicine Lake's a very interesting one because, first of all, we have somewhat of a bigger recharge area, but we have a very high discharge rate. But it's part of Medicine Lake volcano system lies in a rain shadow, and so our precipitation amounts are a lot lower. And so this suggests a very high amount of that precipitation has to go down into recharge the groundwater system. And this is a real surprise to anybody who does hydrology, classic hydrology, because in alluvial systems you would never anticipate more than 20% of the annual precipitation going to recharge. I'm suggesting, in some calculations, conservative calculations, you can go up to 90% of the annual recharge has to go down into spring discharge. That's a very high number. However, if you ever walk that area, you realize there's some features that promote those kinds of recharge rates. First of all, there is no surface drainage coming out of the Medicine Lake system. I've been up there during very early June when the snow's melting, and you don't even get trickles running down the slope. You literally, the snow just sits there and disappears right down the porous volcanic or the permeable volcanic rock. There is no soil profile because it's very young volcanic rock, and it's had no time to really develop. And of course, the high permeability I've emphasized already, and there are numerous lava tubes up there to promote rapid infiltration. So in some ways, the working model for a system like this is that it behaves like an underground river system. And you literally have a series of tributaries all feeding into main stem flows in the subsurface. So one of the things we set out to do with the cooperation of a local landowner up in Fall River Springs is to start conducting some baseline studies of some of these spring discharges over the course of a one-year period. And in this case, we set up staff gauges at 3 different spring discharge sites. And it was important to establish the variability and the discharge rate of these springs over the course of the year and how that's related to precipitation. Secondly, we also measured water quality on a regular basis, as well as the isotope tracers to see if any variability in those tracers and hence recharge source were occurring over time. Here's the annualized plot for the stage data as it's compared to precipitation data for one of the springs. This spring discharges at about 40 cubic feet per second. It's known as Rainbow Spring. It's completely separate from any kind of surface water drainage, so it's a standalone spring. It's very well controlled, and staff gauge levels were measured on a regular basis by trained personnel who work out on the ranch that this study was conducted. The important thing I want to point out here is in gray is the accumulation of snow up on the Medicine Lake volcano. This is from the U.S. Bureau of Reclamation precipitation gauge, and they have both a snow pillow design as well as doing tip bucket rain collection. So we have both rain and snow up here. And albeit it was a very low precipitation year, but we did have pulses of snow accumulation during the winter, and then again this current rain year. In red here are the stage levels for Rainbow Spring. Now you got to realize Rainbow Spring is 35 miles downhill from the precipitation gauge up on Medicine Lake volcano. But you can see that the water levels, the water elevation in this spring tracks nearly 1-to-1 with that precipitation that's occurring up on the mountain. So there is a direct connection. Okay? And I want to emphasize this because, firstly, the direct connection suggests high permeability, okay? And 2, the direct connection suggests that there isn't a lot of storage and dispersion of that pulse of recharge that's occurring, okay? As a matter of fact, you can see what is typically a recessional curve. As the snow is melted, you get some sort of decrease, but there is some sort of delay in that decrease, known as a recessional curve. And that duplicates very similar to a surface water drainage kind of response to a rain event. So I want to set up Ate here just a little bit. He's going to talk to us about age dating of groundwater, and certainly some of the challenges up here. This is some of the results from this publication we put out last year. And what I want to illustrate is the age dates as derived from the tritium helium-3 method suggests somewhere between 10 and 30 years old for these groundwaters emerging at the Fall River Springs. And if you take a look at just the 30-year number here on the left, the reason there's uncertainty about that is because we have an interference from volcanic helium that is picked up by the recharging groundwater up at Medicine Lake volcano. Nevertheless, if you just take that 30-year number and you take the 35 years or 35 miles of travel distance and the elevation gradient between Medicine Lake volcano and Fall River Springs, you come up with a hydrologic parameter known as the hydraulic conductivity. And that hydraulic conductivity you calculate is about 2 to the minus 3 meters per second. And that falls right in within the range of young volcanic rock type of aquifer response to groundwater flow. So nothing unusual here. This is behaving exactly the way you would predict. Now in terms of storage, here's an example from the 87-92 drought for the rising river system of the Hat Creek Valley. And you can see this is a normalization of discharge starting from 1987. But you can see a very significant drop in the discharge rate during that drought period to suggest that the storage amount's fairly low and the response to low precipitation is fairly rapid within this system. And so it's anticipated from this data as well as the previous data I showed you from Rainbow Spring that any kind of climate variability or changes in the water source will have a direct response on the spring discharge rates. And just to emphasize the long-term decrease in flow, this is the pooled area in Rainbow Spring, and you can see the salt deposits on the trees with the red area, pointed out with the red arrows. And the point being here is that there's been a prolonged decrease in the discharge rate of this Fall River Spring as shown by those salt deposits. So I have some recommendations which we can discuss in the question and answer period if you like. First of all, in order to characterize these volcanic spring systems and really understand the extent of their importance to the hydrologic budget up here in Northern California, and also understand the relation to any alluvial basin they may be adjacent to, we really need to understand the precipitation a lot better. What's the input function to these groundwater systems? And I'm a strong advocate of monitoring discharge out of these springs. You can do staff gauges, get community support and volunteer support to record water levels in springs, particularly for lower priority springs, but then invest in real-time data logging systems for the most important ones. And we need to better understand the geologic and topographic controls on some of this recharge and subsurface flow leading to these springs. My hypothesis is that there's mappable geologic controls of that flow. It behooves you to do water quality and isotopic measurements to understand how spring sources change over the course of a year. Some springs may be composites of different recharge sources that you can pick up by doing regular monitoring of these parameters, or some may just be a single recharge area that's very uniform. And really understanding those differences are important. And then based on that, having the age data over the course of a year in the spring discharge is important, because if the age of that water is changing over the course of the year, it suggests different parts of the aquifer volume contributing to that spring discharge. That's something that needs to be understood in terms of the storage amount in these aquifers. With all that great data, we should be able to compute some aquifer volumes and get a good quantitative understanding of the vulnerability of these systems to any kind of change, environmental changes. And that's it.